everyone, welcome to you. Hi the Deep Guy, hi the Greg, hi the Happy, hi the Siphon, hi the Mike, hi the Stump. Hold on, just had to check if my microphone was working properly. Hi there everyone and welcome. And since you're going to sleep soon, Mark, then I'm gonna say hi to you already, and I'm also gonna say bye just in case. And how do you make it? Hope you're doing well. Just want to say hi again. Hope you have a good and fortunately proceed to live good life, everybody. Alright, bye Deep Guy, understandable, hi the Pillar. So the thing is, we are so back because I am in fact feeling well. And the sense of catharsis after, you know, having an incredible stomachache 2 days ago and an incredible headache because of that a day ago is incredible. It's just truly something. And so, thus, and then, and right here and how, today I thought it would be no better time than to walk in the video. Make having a good day. I am having a good day. Well, to be fair, 2 days ago I was also having a good day. It's just that I got massive stomachache for some reason. But today I am having a good day with no strings attached. Make it what the time you are. Exactly. It takes more than a little bit of pain to keep me from making videos and live streams. Also, that is in no small part. I'm pretty certain the headache I had was at least a bit psychological. It had to be because it was so weird. I'm pretty certain it was because of stress. It felt like it. It felt like a stress response. I can't really... I'm having trouble describing it. It just... You know how sometimes when people get stressed, they like... It manifests as pain? What was that except in my head? So yeah. And so... not gonna lie, talking on Discord help. That's nice. Let me play some music first. There we go. And remove this one. Open up. And add this one to this one. Like so. Is that a pie of pie? It's a slice of pie, yeah. There we go. How do you mean OBS disconnected? Yeah, you better reconnect. You better. Pain leads to a headache. I suppose that's true. I suppose I just felt it. Okay. Ah. Well, hi there everyone. Yasley, make it one the time you are is what I needed to hear though. That's the exact sentence I needed to hear. Finally, someone gets me. So, I thought today we could just, you know, walk in this video. Script the up and down quark segment, hopefully animate some more. Oh, animation, right, we have made an intro animation yesterday. Why do I get ads on the stream so often? I don't know, it's YouTube. No, that's the wrong file. That's incorrect. That is in fact not the correct file. The in fact correct file is elementary particles, quarks, even though this isn't quarks, this is an ice cube, which shouldn't even be in quarks, it should be in the intro. It should be called intro. There we go. This is the animation we made yesterday, which is just a cube of ice. An ice cube, if you will. Hi the Iron Voltage, welcome! Welcome y'all. And yeah, last time I'm pretty certain we rendered all of it, correct? Yes, we did. Which means next we will have... We could also start editing the video, kind of. Is this art? Oh yes it is. Oh yes it is. You know what, hold on, I need to turn off the stream for 1 more second because I should make a Premiere file for this. Because we could record it right away. I really want to get quicker and better at making videos. That's because from now on I'm trying to do YouTube a bit more full time, so if I want to do YouTube a bit more full time I have to get better at making stuff. Elementary. There we go. And we're ready. Make it one of the greatest entertainers, in my opinion, because it's between the fast pace of YouTube type videos and slow, relaxing videos. Thank Make It. You're welcome. I am amazing. I do agree. I am fast pace and relaxing, which, I'll be honest, my boyfriend does not like that, but oh well, it happens. Never changing without buff avatar. It's the most accurate one. It's the most accurate one I have, Greg. I know what I can tell you. It's just, you know, we want to go for realism a bit. And so, oh my goodness, Lie groups today. Right. Lie groups, I forgot. Hi there, Kim. Lie groups. That's what we're gonna be doing today. Oh, that's festive. I just literally learned about groups. Speak of the math and the devil shall appear. Hi there, Reblux. I see the blue nickname Curse got to you already. It's real, yeah, it's real. It is real. I can just mention that we'll be doing it for Quarks, and Remco will appear. That's just how the blue nickname works. League groups, exactly. League groups scare me. Well, Iron Voltage, I've had, yeah, I know, same. But fortunately, we don't need to go in depth. That's what's really nice about them. We do not need to go in depth, although, oh, damn it. I don't think we'll get the answers we're looking for right there. I think we have to go for Quark. And maybe history. Do we have Lie as families? I'm sorry, isn't no history of... Did I get it wrong? Eightfold Way, yes. Wait, do we even need Lie groups? Am I an idiot? Understand definition, you need love physics. If you don't know the purpose they serve in physics, we don't need to learn all the math I need. Oh, I definitely will need to learn all the maths. That's definite. I think I might have just been delusional though. I don't think we'll need Lie groups. But we will need groups, certainly, because that's the theory, but I don't think we'll need Lie groups. Independence Understanding proposed the idea of 1961, which is hilarious whenever that happens in science, surprisingly often. Why did the groups lie? Because it's really such a bad. I'm all for it. Physicists believe that they had a good understanding what the smallest bits of matter were. They were electrons, protons, neutrons, and photons. Haha! Fools they were. The components that make up the vast part of it. Yeah. Along with the handful of unstable. They undergo radioactive decay. Exotic particles needed to explain cosmic rays such as pions, muons, hepatitis, neutrino. Discovery of the positron suggests that there could be antiparticles for each of them, or the strong interaction must exist to overcome the electrostatic repulsion in atomic nuclei. Not all particles are influenced by the strong force, but okay, so this is basic background. Got it. Group representation theory. There we go, is the mathematical underpinning behind the Eightfold Way, but this rather technical mathematics is not needed to understand how it helps to organize particles. Hell yeah! Oh my goodness. This technical mathematics is not what I wanted to hear. That is the top one thing I wanted to hear from this page. Mwah. Love it. No offense, I don't know groups, so I really want to avoid them as much as possible. Particles are sorted into... Well, I do know what they are, at least. That's something. Particles are sorted into groups as mesons and baryons. Within each group, they are fully separated by their spin angular momentum. Symmetrical patterns appear when these groups of particles have their strangeness plotted against their electric charge. This is the most common way to take these plots today, but originally physicists used an equivalent pair of properties called hypercharge and isotopic spin. The latter of which was known as isospin. The symmetry in these patterns is a hint of non-lying symmetry, strong interactions between the particles themselves. In plots below, points representing particles that lie along the same horizontal line share the same strangeness as, while those on the same left-leaning diagonal share the same electric charge. Okay. No, yeah, I should switch to dark mode. Right, yes, so sorry. There we go. So we have this, for which we have... That's strangeness, correct? S. We have strangeness. 1, 0, negative. Hold on, my YouTube just crashed because I switched to dark mode and just gave up. I can't see chat. There, now we're back. So, we have strangeness, and then we have electric charge. That's curious. It's really curious. Oh, how good it feels to stretch without just dying. Okay, this makes sense, I suppose. Now mesons. The original way mesons were organized into octant singlets. This is one of the finer points difference between the eightfold weight and the quark model it inspired, which is the mesons could be grouped into nonets. The eightfold way organizes 8 of the lowest spin mesons into an octet. These are chions, pions, and eta mesons. Okay, so far, I'm with you. The American opposite particles diagram an antiparticles one another, while particles in the center are their own antiparticle. Okay, with you so far. Then we have baryons. So this is, but why are we organizing them? Abstract 3-dimensional vectors. Oh! Oh, that's really cool if that's how... Okay. There's an abstract 3-dimensional vector space of up quarks, down quarks, and strange quarks. That's mathematics. That's not even physics. That is such a mathematical approach to it. Remember how yesterday Reblax, well, Reblax remembers, but everyone else, remember how yesterday Reblax mentioned the oh, this is the same thing. Well, the same approach. Maker's not dying till he knows all science. Exactly. Only then can I die. And laws of physics approximately invariant and independent of the attention. The space on that's called flavor rotation, where A is SU. Okay. So unitary transformation to space. Which one is unitary? Is it the one that doesn't introduce any curvature? Linear asymptotes that represents the inner product. That's curvature, correct? As in doesn't introduce curvature? I think. Equal to inner product after transformation. Inner product, that's the cosine, which means so angle basically. Something that preserves angles and lengths. Alright, so basically shifting, rotating, and no, scaling wouldn't be it, would it? Uniform scaling, no. So shifting and rotating, I think. Shifting is not allowed. I mean, moving. I don't know if we're thinking of the same shift. As in... Hold on. So if we have a plane, then this is allowed because if we have 2 points on that plane... How am I gonna represent 2? Oh, you know what? I can represent 2 points for just a sphere. I am good at this. Look at that. Ah, look at that. I am a professional. So this is allowed. You need to keep it at 0, 0. Oh, I see. Okay, so this is allowed. Is this allowed? Because this changes the distance, right? So it's not. What else than rotation would... Scaling is linear. Oh, preserves the inner product. That's right. Okay, so... Changes the lengths. Alright, okay, so what else would be except for rotation? Rotation makes sense. Because, well... It stays in place and the rotation in... 3D space. It's on rotations. Okay, that's good then. That's good. That's all we need. Because right here we're dealing with a 3D space. 1, 2, 3. Well, abstract 3D space. It's not coordinates, it's quarks. So that's fun. Boy, that's an insane thing to try to explain to someone, isn't it? Imagine a space in which each position isn't a position, only it's a mix of up, down, and strange quarks. That would be madness. And they're applying them in the intergenerative space, and it's called flavor rotation. Okay, I now understand why it's flavor rotation. That explains it. Invert the space around like a sock, that would be interdeterminate. It's a new. Okay. I see. So, flavor rotation because we rotate. That's all I need. Okay, SU refers to Lie group of... Oh no. Piss off with the Lie groups. 3x3 interdimensionally determinate 1 special integral group. For example, the flavor rotation this. Just means that simultaneously turns all the up quark in the universe into down quarks, vice versa. More specifically, these flavor rotations are the exact symmetries if only strong force attractions are looked at, but they are not truly exact symmetries of the universe because the 3 quarks have different masses and different electroweak interactions. Okay, let's read that again, because I didn't understand the thing. Is it transformative that simultaneously turns all the up quarks in the universe into down quarks, vice versa? More specifically, these flavor rotations are exact symmetries if only strong force interactions are looked at. But they are not truly exact symmetries of the universe because the three quarks have different masses and electric... Makes sense. Yes, so from a strong force point of view, it is the same. There's no difference. However, it feels the mass is different. So the strong force interactions between them would be exact same, except the masses won't be the exact same, because different quarks have different masses, and we just switch the name them around then. Don't mind me, I'm just doing stuff. Mother Victor X. Yeah, so makes sense. This is for which video? This is for elementary particles video. Well, elementary particles. Anyway, right, this is for flavor symmetry. Okay. Connection representation theory. Assume you have a certain particle, for example, a proton in a quantum state, ket of psi, if I'm not mistaken. You liberated me from me drawing for the first time in my life. What's wrong with you drawing? Drawing seems fun. Why do people who study at night don't get scary down cycles, but I get them even if I don't study at night? Because it depends on the amount of sleep you get, not the cycles themselves. Which means that you can study at night, but then you have to sleep during the day. You have to make up for it, otherwise you get the circles. Also, maybe they just are extremely positive and, they just don't get stressed much, or also, maybe they just need 6 hours of sleep a day. I've never done it, I'm so frustrated. Try again. Try until you succeed. Hey, listen, I didn't get to the videos I'm making in a day. It took me 4 fucking years. If you get to good drawings in less than 4 years, then you're already better than me. So you can keep that in mind. So, one of the rotations A to a particle when the new quantum state recall A this. Makes sense. Oh, I love it. Okay. Depending on A, this new state might be a proton or a neutron or a superposition of a proton and neutron. A superposition. It's fine. Superposition of a proton and a neutron of various possibilities. The set of all possible quantum states spans over vector space. Representation theory is a mathematical theory that describes the situation where elements of a group, here the flavor rotations A in the group are automorphisms of vector space. Therefore, by studying the representation theory of SU3, we can learn all the possible for what the vector space is and how it's affected by flavor symmetry. Rotations A are approximate, not exact symmetries. Each orthogonal state in the vector space corresponds to a different particle species. What's an orthogonal state? Might do to vector particles. Okay. Look what transformations might do to vector. That helps. What's what did I just say? What's an orthogonal state? I'm starting with hard drawing. It may not have been the best idea, but I'm starved as I am. I'm going to finish it even if it takes me 20 hours. If you're starting with a hard drawing, then I don't know if you should do it in the first try. You should give it a couple of tries to not get too frustrated. A state is a vector, so it's a general notion. Okay, two vectors are orthogonal if their inner product is 0. Oh, so if they lie on the same line, basically. I'm trying to imagine it graphically. So if they lie on the same line, then they're orthogonal, right? Which means that would check out. That would actually check out extremely well. Because then perpendicular. I'm sorry. You just said that if their inner product is 0. A real vector space or a complex an operation called inner product. A scalar. I hate when that sort of thing happens. Just give me the simple explanation instead of just telling me what's useful. Abstraction of the usual dot product you may have learned about. Okay, so inner product. What's an inner product then? Arc cosine of the angle between two vectors defined using an inner product. Oh no, there's an angle defined using an inner I'm an idiot. Angle of 90 degrees. Okay, that's good. That's good then. 90 degree. Okay, that clears it up. Perpendicular makes sense now. So then going back to it, orthogonal state in the vector space corresponds to a different particle species. Each orthogonal state. So that would be, wouldn't that just be 3 of them? Or am I an idiot? Or 6 of them rather. Wouldn't there only be 6 orthogonal states in a vector space with 3 values? For each starting state, of course. So if we start with some sort of state, we only have 5 other orthogonal states. Kind of saying in a way that 2 particles have an angle between them. Yeah, an angle of quirkiness. Quirkiness, I don't know. I mean, they have an angle between them in the sense that of different... It makes sense in my head. I don't know if it makes sense for anyone else, but it makes sense in my head that they would have an angle of 90 degrees between them because, like, a top quark is completely different from a down quark. Or rather, the up quark is completely different from a down quark, which means they need to have an angle of 90 degrees between them. Become way harder to grasp. Okay, to be fair, this isn't a simple, understandable concept. It's quarks. There is no world in which quarks could be simple and understandable. Actually, I just come up with a great bit for a video. For quarks, we're gonna do it 2 ways. So first, quarks. For quarks, we have 2 ways to understand them. The basic way and the accurate way. The accurate is purely extremely complete painful. Just skip. So we'll just use the basic one. The basic one is we have up quarks and down quarks, and they make protons and neutrons like this. Okay, that's it. That's gonna be funny. Anyway, enough physics, but I feel confident saying that the concept of an angle is easier in the plane than between 2 particles. Yeah, but the thing is, Reblax, these aren't really particles in the classical physical sense. So like a particle of dust, these aren't really these kinds of particles. That's kind of... This is way more akin to a photon than an actual particle in the English language. So basically, when you think of a photon, it's kind of meaningless to think of it as a particle because it's not really a particle. We call it a particle, but it's not really a particle. So quarks aren't really, tiny objects. They are more like they blur the line. They blur the line between an object and a concept. And because of that, this might genuinely be the most obvious way to think of them. Like, thinking of it as a vector space might genuinely be more obvious than thinking of it as an object, simply because if it was an object, then why antiparticles? I don't know, I'm not great at this, I don't understand yet. Okay, so wait, so am I getting this right? You can only have 6 orthogonal states, because you need 90-degree angle between each of them. In this case, obviously, I mean 6 orthogonal states. Quarks. Well, let's see you, Kim. Kim, go ahead, pronounce the word quark. Go for it, go ahead. Yeah, go on. We're all waiting. Prove yourself to the class. I'm very comfortable with vectors, I think they are very concrete. I may be biased by 4 years of math. I really want to make sure though, before I go on, that my understanding is correct, that you can only have 6 orthogonal states, and that would be basically like, in Blender actually, it will be this, basically. Like, these would be orthogonal because they have 90-degree angle between each of them, and you can't have a 7th one simply because there's no place to fit it. I'm waiting for confirmation because I don't feel comfortable moving on. I'm terrified of this math. This is like physics mathematics. Why do subatomic particles act so weird? Are they just a bit quirky? If it's a pun, then good job. If it's a genuine question, then it's because subatomic particles are, well, protons, neutrons aren't really, but the smaller you get, the more of a concept it becomes. I will make a video about that soon too, but that's the answer for now. But bear in mind that x and y are 2 connected vectors, then x and 2y are also orthogonal. So technically speaking, you have infinitely many orthogonal vectors. Okay, yeah, that makes sense. That makes sense. Technically speaking, you have infinite amount of orthogonal vectors. That's because each orthogonal state in a vector space corresponds to a different particle species. So no, I think in this case they mean 6. Is a plane that contains blue and green vectors. Yeah, but in this case, in a vector space. No, I can't imagine a vector space which would allow me to only take 2 vectors. Rather, I can't imagine a logical vector space in this case that would allow me to only take 2 vectors. But in this case, this is particle species. I don't think there are infinite, or maybe, no, it wouldn't make sense to have infinite particle species just because of the... You know what, I'm just gonna move on reading and we'll see. In example above, when the proton is transformed to every possible flavor rotation A, it turns out that it moves around an 8-dimensional vector space. Those 8 dimensions correspond to 8 particles in so-called baryon octet. Proton, neutron, and the rest. Oh! Hold on. Oh, my goodness. I was joshing around, it makes sense. Oh, I was just joking. Why does that make sense? Around an n-dimensional vector space. Wow, okay. Okay, let's go for it so far. Every Lie group has a corresponding Lie algebra, because why not? And each group representation of a Lie group can be mapped to a corresponding Lie algebra representation on the same vector space. The Lie algebra Oh, I hate it when fancy letters come in. It's always bad sign. Can be written as a set of 3x3 traceless Hermitian matrices. Physics generally discusses presentation theory algebra of Lie group, since form is simpler and the two are ultimately equivalent. Okay, Lie algebra. And Lie algebra. Okay, so it's both. Cool. Basically saying that there are a way of rotation to do stuff like 8-dimensional vectors in a way that works well. Yeah, I mean, as I mentioned, it makes sense to me, where each, like, dimension is just a different particle, and so when you move a proton along this 8-dimensional vector space, it changes the particle. Talk real quick on this code. Oh, please do, go right ahead. I'm all for it. I need it. I need. Listen, yes, Lie algebra. Oh, please do. Hold on, let me open up the... Hi there, Reblox.
Alright, hello. Great. So... Let me get the math board real quick. Alright. Great. So, look at the sphere.
Mm-hmm.
Alright, so a Lie group is a group, but also a geometric thing.
As always, in mathematics.
As always. But also, it's not any geometric thing, it's a smooth geometric thing. So if you zoom in on it, it looks like
a plane.
Euclidean space.
Okay, never.
So if you zoom on a sphere, it looks like a plane.
Right.
No, it's a group, so it has a group operation. And obviously, we just don't say that, oh, it's a group and it's also a geometric thing. We actually require the two to kind of be intertwined, so it's interesting to study. Mm-hmm. And basically, the group operation induces what's called a Lie bracket on the space you get when you zoom in on your Lie group. It's called the tangent space, because basically if you zoom in on this point of the sphere, you can kind of think of the space you obtain as being this one, like this plane. It's tangent to the sphere.
Yeah, makes sense. If you zoom in
so a Lie algebra is basically Euclidean space, but with a Lie bracket. And so if you look at a Lie group and you zoom in on it, you get a Lie algebra, and that's what happens. And I think if I'm not mistaken, the 2 point of views are equivalent. So studying a group and studying its Lie algebra is the same thing.
Yeah.
All right, I should also maybe say something else. Technically, maybe it would depend on which point you pick on the Lie group. So usually we just pick the identity element, if I'm not mistaken.
All right.
So you zoom in on the identity element. It looks like Euclidean space, and the group operation induces what's called a Lie bracket, which is some kind of operation between vectors of the Euclidean space, and it makes a structure called a Lie algebra.
Mm-hmm.
Hello, Duck.
Hi, detective. Oh, he said hi to you, not to me. Oh, fine, whatever. See if I can. All right, go on. So
Lie algebra. It's actually pronounced Lie. I thought it was pronounced Lie at first.
Yeah, it is. Yeah. So Lie algebra. So what is it exactly? Because you said that it's when you... I'm still having a hard time understanding exactly what Lie algebra is.
Well, basically, it's a vector space, so like a plane or 3D space.
All right. So,
thing, but with a special operation on it that is related to the group law.
Oh, I see. So when you have a group...
if you go on the Wikipedia page, they'll probably explain exactly
okay, so
what we care about.
If I understand correctly, when you have a Lie group, since it's a group, like the smooth group, since, as you always say, it's also a geometric object, I believe, then if you zoom in on the geometric object, then that's... I can see the transformation to algebra, from a group to linear algebra. I don't know if I'm getting it correctly, but I can see the switch, rather the lack of switch. However, so wait, hold on. So Lie algebra, would it be like a algebraic approach to transformation? Possible transformations?
I mean, everything is algebraic here, so...
Yeah, I guess fair point, damn it.
But yeah, I'd say that a Lie algebra is probably less geometric than the whole Lie group.
Could you give me an example, maybe? Would that be possible?
I can try. All right,
Okay.
so Lie group, Lie algebra correspondence. All right, so do I have a simple to easy to understand example? Example. Yes, great. All right, great. All right. So do you know about matrices?
A thing or two, yeah. I've seen them once or twice in my life.
Do you know how the product works? That's all I ask for.
Product, I may not know
Matrix
the name
product.
of it. So which one is
The
it?
matrix product is basic. The usual matrix product where you kind of, I mean, there's only really one thing that's called the matrix product. There are some other
Yeah, I
ones
mean,
that
I
are
may
always
know it.
useful,
It's just that I'm really bad remembering names of mathematical tools, so I don't.
But basically, the thing where if you've got A, B, C, D, and W, X, Y, Z.
Oh, so two matrices together, matrix product. Okay, that makes sense.
Matrices
All right, then I do know it. Yeah.
Right. So you've got also the identity matrix, which is this one. And it's the identity element for matrix multiplication. Multiplying by the identity just gives you back the same thing.
Right.
Now you can look at all matrices A, B, C, D such that there is some other matrix with other entries. And when you multiply the two together, it gives you the identity matrix. So these matrices are called invertible matrices.
Makes sense if you get back the identity.
Yeah, they have an inverse, basically. And actually, n by n square matrices that are invertible actually form a group. And what's more, they even form a Lie group. They're a geometric object, so obviously it's hard to represent because you need square matrices, and if you've got only one entry, then it's one-dimensional. It's not interesting because it's basically just plus or minus one. Well, it depends on your interest, not plus or minus one, but basically it's not really that interesting. And if you've got 2x2 matrices, then it exists in 4D space, so it's obviously quite hard to represent.
Just draw it really quickly on a 2D plane.
A Lie group.
Okay.
Basically, you can look. So it's a geometric thing, and every point of the geometric object is secretly a matrix. That's the gist of it.
Mm-hmm.
In particular, the identity matrix is in the group because, well, the identity element of the group is in the group. That's required. And so you can, geometrically speaking, zoom in on what's around the identity matrix. Basically, what you get, like as an operation, so I mean, I could give you the rigorous definition of what a tangent space is, but it's, yeah, I can give you an idea. Basically, you can take a path around your geometric thing that passes through the point that interests you, and you can look at the derivative of the path at this point.
Oh, and then from that derivative, you basically get like a gradient to see what the...
Yeah, it makes a vector and it's tangent to the geometric thing. So all possible vectors that can be obtained this way is what we call the tangent space. That's the true definition of it, basically. It's like in physics. It's like in Newtonian mechanics when you have some object that spins, like on a pendulum. Well, its speed is always tangent to the. If it's a pendulum, like it's stuck on a circle, then its speed is always tangent to the circle.
Right.
It's the same thing.
Yeah.
Speed is the derivative of position. That's the same concept. That's why physicists really like differential geometry. Like it makes sense.
Okay,
right,
but then so this basically lets us like get the not object, so identity. What did you say it was? No, I mean this
Yeah.
one in a Lie group. What is it? You said the word a second
Um,
ago and I already forgot.
hang on.
This thing
Are
in
you
the
drawing on the web?
this thing
Yes.
in the Lie group
So
is
this one is the identity element of the group.
okay. So when we have the identity element, now we have a way to
yeah,
find the elements around the identity element. Am I understanding that correctly?
yeah, we have a way
Okay.
to.
So actually,
It's
no,
not
no.
really
I'll
around.
just
It's
let.
more tangent. It's not really the same thing, but basically, the Lie group. Let's call it. So its true name is GL2, and let's say that we've got real entries in the matrix. So these are all invertible matrices that are square and 2 by 2.
Mm-hmm.
And it's contained within all possible 2 by 2 matrices.
Makes sense. Yeah, because there has to be.
Yeah. And so, well, this is actually a 4-dimensional vector space, and like that makes sense. You've got 4 numbers,
Yes.
4 entries, and you can basically say that the matrix A B C D is A times the matrix 1 0 0 0 plus B times the matrix 0 1 0 0 and so on. So it's basically 4D space, but you've got a cool product on it. And so when you look at the tangent space around the identity, the tangent space of GL2 of R around the identity, it's made up of matrices.
Yes. Okay. With you so far.
And then you get, so the group operation, like matrix multiplication, actually gives you an operation on these matrices, and it's called the Lie bracket. So it takes in 2 matrices, let me call them, let's call them M and, well, let's call them A and B. So these are 2 by 2 matrices. And the Lie bracket of them is a third matrix, and here it's given by A times B minus B times A.
Mm-hmm.
So that's an operation on matrices that are tangent to the identity matrix, basically.
Yes.
And so you can think of, you can think of basically so one of the I never formally learned this math, but basically thinking of Lie groups and thinking of their Lie algebras is the same thing. So when your Wikipedia page says that you can work with SU of 2 or with the Lie algebra, which is also called SU of 2, but with a different font that I can say.
If I'm gonna be completely,
it's fractal letters. So
I'm
with
gonna be
matfrac
completely,
SU of 2, it's the same thing basically.
I'm gonna be completely honest with you. I don't think my understanding is the correct one. I have
What do
been
you mean?
nodding the entire time because I kind of understood what you're saying, but I think I'm wrong. Can I? Okay, so the way I imagine it, right, is that you have this identity element. I'm gonna simplify it into a 2D space. Imagine it's was it 4-dimensional or would it be 6? No, 4-dimensional. That being the Lie
Right.
group, right?
The Lie group is a thing within 4-dimensional space. It's not the whole space.
Yeah, yeah.
Like the
So
sphere is a thing
yeah,
in
I mean,
3D space, but
so we
it's
have this identity element in a 4-dimensional space, or rather, we have
yeah.
this identity element in a Lie group that's in a 4-dimensional space,
Yeah.
and then around it we have different matrices that.
It's not really around it. It's more tangent to it.
Okay, what's the difference? I
It's
feel like
like
that's important. I feel like
yeah.
I am.
Yeah, it's important because basically the matrices that you're going to get are not necessarily in the group themselves.
Oh, yeah.
They may not be
Okay.
invertible. These are just other matrices that are
Okay, but then
there
what?
because of geometric thingies, basically.
Okay, but what then? Why are the matrices next to it then?
They're not next to it. Well, basically, they're
Right
not
tangent
really next
to it.
to it, but I mean, look at what I drew on the sphere.
Or are they not
So
why
you've
are
got
they next to it? Only why are they there? Oh, that's like I said.
Well, for instance, take the sphere. The sphere is all vectors that have length 1.
Mm-hmm.
For instance, around the origin, which is somewhere around there. And when you take a path on the sphere, so the thing I drew in black, that passes through the point that interests you, so the little x, you can look at the derivative on your path at this point. And it gives you another vector which exists in 3D space, which I drew in red.
Yeah.
But you know that vectors, they don't really have
Direction.
they have a direction. They have basically they don't really depend on. We don't think of them as depending on the point where they're started from. So
It's
basically,
three numbers
you
basically.
can say that this vector is really this vector.
Yeah, I mean, in my head, I just think of it as like X, Y, Z. So it's more like where the end arrow is. We don't. If we wanted to also account for where it starts, we would then need like another vector A, B, C. This time defining the point where it starts. It's okay.
Yeah, that's this.
Get
so
that.
The vector you end up with when you derive your path, it doesn't really need to be on the sphere, no, does it?
Yes.
Absolutely doesn't. Like, well, in my drawing, it's obvious that it's not on the sphere because it's too small. But basically, you could also say that so that's just calculus. If you multiply a function by 2, you also multiply its derivative by 2.
Mm-hmm.
Yeah. So if you take the same path but you imagine that you go twice as fast, you're going to end up with a vector that's twice as long.
Okay.
Yeah. And if you try to go the opposite way, you're going to end up with a vector that's facing the opposite way.
Right.
Right. So basically, tangent vectors themselves form a vector space, like you're allowed to add and scale them, basically. And so that's why it really doesn't need to stay within the group. Because, well...
Wait, what is the group in this analogy?
in the analogy, the group would be the sphere itself.
Okay, and so what is that path then we take?
A path is, well, if you've got a geometric thing, a path is just a continuous function. We need to derive it, so we assume that it's differentiable. So it's a differentiable function from the unit interval, well, from some interval in R to the geometric thing. Basically, a path is just I mean, it makes sense, but maybe it doesn't to you because well, it's not. It's.
I mean, no, I mean, like, I don't quite understand what the path would be like analogous to the matrices example.
Well, a path is just a function that has some nice properties. Basically, it starts from I mean, let me simplify it. Basically, it's.
Oh, it's like a function
interval.
on a. Oh, that doesn't make.
Yeah.
What I'm gonna say is not gonna make sense. It's like a function on the group.
It's not on the group, it's to the group.
It's not gonna make some. Okay, function to the group. So hold on, wait. Wouldn't this be actually a really good way of showing the same things for quarks? Because with quarks, we do have a three-dimensional space: the upness, the downness, and the strangeness. That is 3 dimensions. So if we have a wait, is that what? Oh wait, but is that the thing that we're grouping? SU3 refers to Lie group of 3 by 3 unitary matrices with the determinant one.
So it's not the same group as the one I showed. Also,
okay, it's 8-dimensional.
SU of 3 is also a little bit more complicated because it has complex entries. Not real entries, complex entries.
Oh, that's fun. Of course, it would be too simple if it had real entries, of course. It's 8-dimensional.
Also, it needs to have determinant 1.
Wait, why is it 8-dimensional? I am so lost.
I can try to give you an argument for this, maybe. So, if you take a 3x3 matrix, how many entries have you got? You've got 9.
9, right.
So we've got 9 dimensions. All right, but then we demand for the matrix to be unitary. No, you can show that it is unitary. How do I? Am I remembering correctly? I think I am.
Wait, is the unitary going to put some restrictions on it that cause it to be able to describe with 8 numbers?
There's not only unitary. There's also other stuff, and there's also the fact that there's complex coefficients.
Yeah, I mean,
so...
as like one of the properties of the unitary being that it can actually be described using 8 numbers because the 9th one can be deduced, for the lack of a better word.
Yeah, you can do that, but actually you lose more than 1 dimension. I think you lose 3, if I'm not mistaken.
Oh.
So we've got 9
sense.
minus 3, we've actually got 6 dimensions.
Where does the 8 go? Okay, never mind, I get it. Okay, carry on.
Why, you want to end up with 8 dimensions, that's right?
Mm-hmm.
Right. Now we also demand that actually. No, wait, do you lose 3 dimensions? I may be mistaken on this. How many equations have you got actually? I can write out what being unitary means actually. So if you take a matrix with some entries, well, I'm going to write them as x. So you've got x11, x12, x13, x21, x22, x23, and so on. What being unitary means is that, have you ever heard of the matrix transpose?
I have, but I don't, for the life of me, I don't remember what this.
Alright, so basically the matrix transpose is just shuffling the entries around. It's more or less, I mean, I'm going to write it out, so you basically kind of reflect the matrix along its diagonal.
Okay.
It may seem kind of random like this, but there's actually it's actually like a really natural thing to do.
Yeah, I'm assuming there's some
but I'm not going to
geometric.
explain why. But we're not just doing this because for shits and giggles. There's actual reasons behind this. And what being unitary means is that the product. Oh wait, they're complex matrices actually. I have to check that I'm not fumbling this. I'll write out the equations, and if I get the number of dimensions wrong, then that means that the complex case doesn't really behave the same as the real case, and so I never actually learned the complex case. The only time I did unitary stuff was with real coefficients, so there may be some weirdness going on here. So you require then to get to be inverses of each other, basically. So you want to end up with the identity when you multiply them together.
Yep.
The reason why this is the same as preserving the inner product is due to what the transpose is, and I'm not going to get into that. But it's the same thing. Oh yeah, also I forget, since we're in the complex world, we need to put conjugates here. That basically require this.
Okay.
And so this actually gives us, well, a lot of equations to work with. So, for instance, if we know, well, we should compute exactly how many equations this gives us. But basically, you can write out as a big linear system of things. And if you count the dimensions correctly, and you add that, actually, I think the determinant one may not matter. But basically, if you count the equations correctly, you're going to end up with the right number of dimensions. That's why. Basically, why it's why it doesn't have all 9 dimensions is basically because being unitary is a lot of equations.
Okay, so basically, if you specify 8 different numbers, then you only have one choice for the 9th number for all the equations to equal.
But actually, you've got even less choices than that. You need less than 8 numbers to figure out what the rest are. And I could compute, if I had some time, I could compute exactly how many dimensions you lose, but don't really want to do that.
Well,
I'm kind of lazy right
I
now.
kind of am.
But that's where it comes from, basically.
Okay.
So what the... how many dimensions does it say it has?
8.
8, yeah. S3 times S5. All right. 8 dimensions. So you start with... all right, I think that's... There's also like something else, is that since the coefficients are complex, and complex numbers are like a plane, you actually start with 18 dimensions, and you lose a lot every time.
Okay, makes sense. You lose most of them actually.
Yeah, you lose a lot of them.
Which checks out.
That's also why you end up with an even number of dimensions, because we can do everything in the complex world, and then you say, oh, so we have this many complex dimensions, and so we have 2 times as more real dimensions, basically. Like,
Okay.
there's a notion about that. Basically, complex numbers are of dimension 1 over the complex numbers, but they're of dimension 2 over the real numbers.
By the way, NK Corp said, I'm struggling with waves right now, and looking at this scares me for what I'll have to look at in the future. You're thinking about studying mathematics? I mean, I'm assuming if you spend enough time, this just becomes intuitive and makes sense. The thing is, I just haven't spent enough time.
I'd say it makes sense. Is it intuitive? Like, if you just gave me a SQ3, would I go, oh, just like it's 8 dimensions? Like, that's it's obvious. I wouldn't do that.
So, okay, I think I understand
if you're determined enough to work through stuff, I think you can make sense of most everything. And if you can't, you go ask someone smarter than you.
I'm crossing my fingers right now that the eightfold way stems from the 8 dimensions, because if that's the case, then it all makes perfect sense why the eightfold way exists. So basically, then we have the Lie algebra, right? And this Lie algebra depends on two, like, it depends on, well, this, I don't remember, I already forgot the operation. I mean, that they had, and basically because of the unitary transform, was it?
So yeah, basically, you've got asking for the matrices to be unitary takes away a lot of dimensions.
Okay, basically. So basically we have a matrix, which is also can be imaginary, which means if we wanted to represent all possible states of the matrix, that would be 18 dimensions. Because we have 9 numbers, then times 2, because can be imaginary. However, because we have this unitary constraint, that's kind of like putting an equation which always has to be true, which means we can exclude like huge numbers of, well, we can exclude most of states because they would break this in quote equality, or literal equality. And so,
I mean, for instance, that's the same. This is a really... There's a theorem in differential geometry that says this for a lot of cases, but basically, if you take the plane, there's 2 dimensions, but if you only look at the circle by imposing the equation x squared plus y squared equals 1, well, you've got 2 dimensions, but you've got 1 equation, so you subtract 1, and the circle is something that looks like a line when you zoom in on it, so it's something of dimension 1.
yeah, or
that's
even
basically what's going on here.
Or even easier, if you have a line, if you have x is equal to y, then that's a literal line. That's single dimensional. So this equation basically subtracts that dimension. That's how I was thinking of visualizing it in Blender as a 3-dimensional space.
If you're a mathematician and you're wondering whether this always works, actually it's not that obvious, because you need the equations to behave well, basically. But everything behaves well here, so the reasoning works.
So then that's how we start with a matrix, which is a 3x3, and that's how we get to 18 dimensions, and that's how we drop down to 8 dimensions. And the part that I'm really hoping for, fingers crossed, is that the 8 in 8 dimensions is also the 8 in the eightfold way, because if that is it, then that's actually extremely simple, because then each dimension would just be a particle.
Representation of S 3.
Since flavor artifacts made no exact symmetry, so not consider it.
I'm not sure.
I mean, hold on. In the example above, when the proton is transformed by every possible flavor rotation A, it turns out that it moves around an 8-dimensional vector space. Those 8 dimensions correspond to 8 particles in the so-called baryon octet, proton, neutron, and then the other ones.
I'm not sure that the 8 they may be related. The answer is I don't know.
This corresponds to an... But like, isn't this saying exactly that?
The answer is I don't know, because it basically a representation is just SU3 are the matrices in SU3 are 3x3 matrices. So usually you'd say, all right, well, they are functions that take in 3x3 that take in three-dimensional complex vectors and transforms them. But here you've got 8 dimensions, which would be complex dimension 4, so maybe it's related to S3 being an 8-dimensional object, but just from this sentence alone, I can say maybe Scarlett knows more about this than I do.
Yeah, actually, you know what? Yeah, I should ask Remco. That's actually...
You should ask them, and you should ask the physics people, because they probably know actually what the representation is.
The thing is, though,
which I don't.
The theory of quarks is more mathematic than physical, because with like historically how it was created was basically we had no experiments. We were just trying to find a way to like organize them. Hold on.
Yeah, that makes sense. But
some help.
But basically, the thing that's missing here is exactly what mathematically the representation is. So I can't really answer that question.
But still, I mean, this seems extremely promising. Those 8 dimensions correspond, because it is those 8 dimensions, 8 dimensions of the SU3. So the 8 dimensions of SU3 correspond to 8 particles in the so-called baryon octet, proton, neutron, so on. This corresponds to an 8-dimensional octet representation of the group SU3. Since A is an approximate symmetry, all the particles in this octet have similar mass. Every Lie group has a corresponding Lie algebra, and then... You have helped me so fucking much. Whoa.
Well, I'm happy to help.
I feel like...
I mean, I love popularizing science and math, so, well, mostly math. I'm not qualified to speak about science, but...
Normally, I would feel like I genuinely would have to skip over this, because this is... it's incredible.
Actually, the thing you're saying, that the 8 dimensions may be related, so that's actually an interesting thing, because, well, we talked about this a little bit in my group theory class. So basically, sometimes you've got a group, and you want to say that it transforms some things into other things, because it just makes sense. Like, usually, I'd say, that's what I said yesterday, a group is the symmetries of an object, so it's related to that object. But sometimes it turns out that it can also be related to another object, and that's surprising. It actually, there's some very very interesting math behind that. Actually, it's on the cover of the PDF of this class, basically. Basically, you've got a group that usually you'd have shuffle 5 things around, but turns out it can shuffle 6 things around. And that's very interesting, because that never happens elsewhere. And maybe that's related to S303. Maybe because S303 usually would have, I guess, a 6-dimensional representation if we're speaking in real terms, because S303 acts on complex vectors that have 3 entries, and so 3 complex numbers are basically 6 real numbers. So maybe the 8 dimensions, like the fact that it can act on vectors with 8 dimensions, maybe that's actually some kind of exceptional behavior. What I'm saying is basically, maybe there are some mathematicians that really like this very much.
The thing is, though, this... Like, I get that maybe. The problem is, this is the kind of maybe that no one watching the video would ever think. Like, the thing is, if you
Yeah.
actually need to know that kind of maybe, or want to be sure that kind of maybe
Yeah.
does exist, this is not even the point at which you read textbook. This is the point at which you just read the papers. This is the point where you go through the 60-page long paper about quarks, and that's kind of, or I don't know, ask a professor who's been working on this. That's
Yeah.
this is actually
I mean, it
surprisingly.
depends on the complexity of like the math being considered. So, I mean, Lie groups are a lot. They're.
I mean,
I may be saying something that's false, but I believe that it's true. And I mean, like Lie groups are not really that new, and they've been studied a lot. So maybe we've actually understood the deep mathematics behind what interests quarks people. But yeah, that's probably not going to be explainable in the video.
yeah. I mean, the
I'm
thing is, I
just
still,
thinking about it because I like groups.
I still really like which mentioned so far because it makes sense. I won't sit here and pretend as if I understand the math exactly, but it makes sense to me. The starting with a 3x3 matrix and ending up in an eight-dimensional space, that makes sense to me. And then if each direction in the 8 dimensions is a different baryon, that once again makes sense. So basically, we're starting with a matrix of the quarks, and then since we're confined by the unitary transformation, from those quarks, so if I understand correctly, we basically have 3 quarks, right? Why am I bringing up paint? We have a whiteboard right here.
Currently, there's 3 quarks. That's the theoretical physics part, which I know absolutely nothing about. So
yeah, but if we have
the right person
3
for this.
quarks with their hold on, let me just find it right here because it's small enough. Yeah, fine. We have the 3 quarks, so basically topness, upness, downness, and strangeness, and like each one of them has its. Oh, my handwriting is horrible in comparison to yours. Each one of them has its own upness, downness, and strangeness. Then what this is basically saying is that this then translates to us ending up with an 8-dimensional vector which specifies how much of a particle it is. So how much of a neutron it is, how much of a proton it is, and then ... there's 8 of them. That's like...
Can you show the Wikipedia page again? Wait, what page is it actually?
This is the Eightfold Way page in the flavor symmetry.
Eightfold Way Wikipedia. I think what you're saying might work. Alright, so you've got your rotation. Alright, so... Oh, alright. So I think you understand what the page is trying to say. So as you've said, you've got your 3 quarks, which correspond basically to 3 axes in the vector space, kind of like blender.
Mm-hmm.
And a flavor rotation, is basically an operation on this space. And since more complex particle, and so basically when quarks shuffle around, it makes... How do I explain this? When quarks do stuff, it corresponds to some matrix, some 3x3 matrix, which is in SU of 3. And then, to explain the link between quarks and particles like protons, you use the link between SU of 3 and the 8-dimensional vector space, which is, mathematically speaking, the representation. I think that's what it's trying to say.
Okay, is it just
Not
me,
exactly
or is this like
yeah.
absolutely awesome? Am I because here's the thing. Am I I don't know if I'm delusional here, but this feels like such an awesome... This probably is the most advanced thing I've ever discussed in a video, and I still feel comfortable putting it in there on the very beginning just because of how awesome the connection is. So basically,
I'd like to know, actually, if you ever find this out, maybe ping me on Discord. I'd like to know what the representation exactly is, if you can find this out, like the link between the 3x3 matrices and the 8-dimension
Oh,
the
I don't think
dimensional vector space. I'd like to know what that is.
I can't. I really want to skip this because this will be advanced. Like, this is the point in which you are, first of all, way more qualified than me, because it's Lie groups, and second of all, I don't. I mean, I could look at it. I guess I could look for it.
I mean, I'm not asking you to put it in the video, obviously, but if you ever find like something
you know
that explains what exactly it is, you can ping me and then
But you know
I'll
what's
happily read it.
truly awesome about this, if I'm not mistaken? The book I've used to start my research on this video has mentioned that the way quarks were theorized was with Lie groups. So basically, the way they were theorized, right, is you started with assuming that there are three quarks, up, down, strange. Then,
Yeah.
assuming that particles have, each one of them has three quarks, so that's where you get 3x3 matrix, three possible quarks, and each particle has three quarks themselves. And then using Lie groups ended up at 8 subatomic particles, or rather 8 baryons. And then, experimentally, it was shown that there exist only 8 baryons. So, I mean, I can't stress enough. This is from one book. I will have to double check that in all the sources. But apparently, basically,
I think that's mostly correct.
Yeah,
but technically, the particles themselves are. Yeah, they would be 8 by the particles like protons and baryons. Baryons are 8-dimensional things. Like they are the 8 entries vectors. And what the 3x3 matrices are quarks basically switching around.
Yeah, so what's really awesome to me here is that we basically proved this. Well, proved in quotes, proved for the first time before the Hadron Colliders, all this stuff. We basically proved this without ever, like, interacting with quarks in any way. We just were like, mathematically it makes sense.
We found evidence for the theory being correct.
Yeah, like, insane theory, and then it checked out. It's so incredible. My goodness, this is beautiful.
I believe particle physics has a lot of times being through this, actually. Like, for instance...
advanced physics in general, yeah. That's because...
When Dirac suggested antimatter existed, like, it was just more or less a mathematical argument, and it was demonstrated, like, way later.
Yeah, because, well, when it comes to antimatter and matter, if I'm not mistaken, it is precisely the E squared is equal to mc squared plus p c squared, if I'm not mistaken. This was the equation that theorized antimatter.
I don't remember the details, but physics bro told me once. Basically.
Yeah, I mean, one of my favorite chapters from a physics book, which is such a nerd thing to say. My goodness, having a favorite chapter in the physics book, that's sad. But basically, one of my favorite chapters in the physics books precisely talks about that. How basically this is the equation you have, right? And because this is the equation, this equation has two solutions for E. You can have a positive E, or you can have a negative E. The problem being that how can you have negative energy? And so basically, from there, it was theorized that since this equation we really believed it to be correct, you need some sort of way, and then you have like the whole quantum fluctuations and just particles upping off. No, it's great. I absolutely love it. But that's kind of how physics is made. Yeah, like the thing is, our technology is behind physics. It's always going to be behind physics simply because of how research works. So you really often need to theorize things and waiting years for the technology to actually exist to prove them in any way. And you also need to develop. You also need to develop your theory. You need to find a way to prove it in a way that actually, you can't interact with quarks. You can't interact with an individual quark. So you need to prove your theory that like checks the consequence of a quark rather than the quark itself. This is amazing. My goodness, I love it so much.
Well, that's great. Sadly, I think I'm going to have to go.
It's fine. Thank you so much, Reblax. I don't want to keep you here.
Always happy to help. And if you ever find out more about the relationship between S303 and the 8-dimensional vector space, do ping me. That sounds interesting.
Yeah, I'm already pinged Remco to ask for help with this.
All right, great.
All right.
Bye.
See
ya.
Bye,
everyone.
Bye. That is so awesome. I'm sorry, am I in the wrong? This is amazing. Is the link clear enough? This is great. I'm gonna script it right away. Let's play some music. Okay, I'm sorry, I just needed a second. Why goodbye happy? Make this game better. I mean, okay, I know I sound like a massive nerd, but I can't them. This is really great. So this would be actually up, down, and strange. This is so awesome. Okay, Eightfold way. I need to triple, quadruple, quintuple check this because I can't have mistakes on a topic this awesome. So baryons first. Baryon. Brilliant example of baryons because baryons are composed of quarks. They belong to the hadron family of particles. Odd number of valence quarks. I'm sorry, valence quarks. Valence quarks. The quarks and antiquarks that give rise to the quantum numbers of hadrons. The quark will now is flavor SU3 of the Eightfold way. They have an odd number. Oh, they have an odd number. Do you12 RPG games? Yes, Skyrim. Skyrim was my first record holder for the longest live stream. I spent 12 hours in 3 days. I spent 34 hours playing Skyrim on stream. 34. It was great. Okay, let's retry it all completely now with the knowledge. How did they come up with strange as a tempo quarks? If I don't remember correctly, it was just because it was strange. That's why. I think it was something to do with microwave background radiation, or I don't know. I don't remember. Initially, for classes of nucleus in hadrons led development of quark model. Both the American. Okay, so. Yeah, okay. Organization. Group theory presented is a mathematical underpinning behind the Eightfold way, but as well technical mathematics is not needed to understand it. Particles are sorted into groups as mesons and baryons. So right here we have meson octet, like this, which, alright, and then we have a baryon octet, and then we have baryon decuplet. Hi, GX Gaming, welcome. You pay out like you by YouTube. Could you play Fear and Hunger? I might, I will. You know what? Not might, I will, in fact. So I like appreciate you saying handsomely like you. I do appreciate that. Development, yeah, okay. So what we want is we want the quark model. Valence quarks. The quarks that give rise to quantum numbers of hadrons. Alright, quantum numbers, which ones are there exactly? There are so many references to the cells. I know it's not circular, but it's close. Particles a bit odd, isn't it? They really are. Okay, we have electronic, nuclear, connection to symmetry, right. Section gives models based on symmetry and variance apply the symmetry ideas originated by Emino and develop. Hi there, Ali. Hi, welcome. How you doing? How you doing? Hi. I'm so lost. This is just. Red Black is amazing. I'm really lost. I need to find like something to pivot with. Because I think I understand the Eightfold way, but this is not. It's not good enough. I need to do better. I need to do better. What am I trying to do here? So my mind is a bit of a ADHD. Modern interpretation. All right. Like a 3x3 interior matrices once per interior, for example, the flavor rotation. On the upcoming vice versa, what's these for rotation? Problem quantum state player. I'm doing, how are you? I'm also doing. I'm doing is the most grind set of just responses you could possibly have. And you know what? I dig it. I respect that. Leon's back representation theory, yeah, set of free traceless images, physics, and discuss the perspective. Okay, since they're almost simply. Okay. So we have this, but that we use in. I'm so lost. Okay. Let me just close everything off, except for baryon. Let's have a baryon. And right here, what we're looking for is flavor quantum numbers. Strangeness flavor quantum number S, not to be confused with spin, was meant to go up and down along the particle mass. The higher the mass, the lower the strangeness, the more S quarks. Particles could be described with isospin projection, related charge, and strangeness mass. We discovered new quantum numbers were made to have some of the description. Behave the same way strong interaction as the quarks. Change us bottomness and topness. Hilarious. Flavor quantum numbers respectively related to the number of strange charge bottom and top quarks and anti-quark counting the relations. This just subtract them together. Cool. However, the problem is there's charmness there. So this sort of 3x3 falls apart for me, which would be pretty annoying if I do say so myself. Committed to a say because all the tabs are important if we should return them. I am gonna return to them, but I want to return to them one by one. So eightfold way. Class of subatomic particles are hadrons, the led development of quark model. Okay, so it's hadrons. Aha! Not baryons, hadrons. No, because molecules were trying to get about electric force, but mass. The pneumatic comes to two hadrons, proton and neutron. Mass of the protons and neutrons and binding energy considered for the okay. Cool. Anti-green. Fun. Quark model. The properties of hadrons are primarily determined by their so-called valence quarks. For example, a proton composed of two up quarks with electric charge this, and one down quark with electric charge of negative 1/3. Adding these together yields a proton of charge +1. Although quarks also carry color charge, hadrons must have 0 total color charge because of non-color confinement. That is, a hadron might be colorless or white. The simplest ways for this to occur is out of a quark of one color and an antiquark of the corresponding anticolor. Or 3 quarks with different colors. Hadrons with the first arrangement are of type meson, and those with the second arrangement are baryon. Okay, simple enough. We have meson, which is anti-green and green, baryon, which is red, blue, and green. That's hence 3, I'm assuming, and anti-baryon, which is anti-green, anti-blue, anti-red. Hilarious to call them anti instead of, I know, violet, teal, and yellow, but whatever. Or light blue, actually, I suppose. It's more. No, it's teal, because in between green and blue, that's teal. So, organized into octets and singlets. So find the positive difference between the eightfold way and the quark model inspired. Oh, so quark model is different. That's not fun. That's whatever the opposite of fun would be. What's a valence quark? I'm sorry, what is a valence quark? And what kind of sense does that make? What's a valence quark? I don't understand. Given the identity properties around each proton and neutron atoms equals composed of 3 valence quarks just around it. Oh, so it's just quarks that. No, wait, see quarks. What's a valence quark? The towers arrangement of these valence quarks would dictate whether a particle is a proton or a neutron. So valence is like just the important quarks of. Also, additional questions. Is a valence quark is like a net surplus of quarks? I'm just gonna save up all the questions I have for Remco. Mental brain, I choose to be the subject. I choose the subject. Okay. Experimental verification beginning in late the model was independently proposed by physicists. This to adapt to quarks in the context of paper. It is in long manuscripts. Also, magical quantification. Today, the model has essentially been observed by the quantum field theory strong electrical interactions. That was not the model. Not really elementary, can be regarded as both valence quarks and antiquarks, which give a quantum number of hadrons. These quantum numbers are labels identifying the hadrons in two kinds. One set comes from the Parameterizing symmetry, and then P symmetry, C symmetry, PC symmetry, CP symmetry. The other quantum numbers has been trained to determine so on. The strong interaction binding quarks together are insensitive to these quantum numbers, so variation of them is to systemic mass and coupling relationships among the hadrons and manipulate. Okay, whatever. See if I care. I do care because I kind of need to. Eightfold way. Then. So strangeness, leveling. Okay, so what is the eightfold way used for? Organizational scheme for class of subatomic particles known as hadrons led development of the quark model. So this is how we organize them into 8. Okay, so what we're basically saying is that there are 8 types of hadrons. Alright. So, imagine a 3D space, except you don't need to imagine it because I put it your screen right there. You are welcome. Hi lamppost. Why might not be a gun and not getting understanding. Did Reblax go to bed? I don't know. I know. I really don't. I need them. I already used Reblax, okay? You need to give him some time to rest. I'll be using them up. Now, in this case, this free space won't spawn to one position. Quarkness. So, have an up quark, a down quark, and a strange quark. Seem a bit confusing at first, but it's a pretty standard way to describe things in mathematics. example, if you've got a fruit basket with oranges, apples, and bananas, then them as a 3D. Yeah. And describe it. 3D space where these apples, these are oranges, and these are bananas. I fear the power of the blue name, exactly. That walks 1 time per day. I just need the stretch. Point in this space will describe a different combination of the 3. Right here, 5 apples, 3 oranges, and 1 banana. Right here, 7 bananas, and right here, 1 of each. Same thing we're doing for our quarks. Right, is that what we're doing? I just want to make sure I fold away, and flavor symmetry. Need to fear the blue names till I'm playing Stardew. Reblax is broken right now, only one walk next stream. Exactly. We only get 1 blue nickname per stream. First, the Lie group of 3x3 unitary matrices with determinant 1. Bye Lampos, have a good one too. Which you can know the value characterizes some property of the matrix and the linear map represented on the given basis. Damn it, I could use Reblax again because this will be also useful for another video. Non-zero if and only if the matrix is invertible. Oh, so if it's invertible, that makes sense, okay. So that's why determinant is... Wait, no. Non-zero if it's... Okay, yeah, then that makes sense. Oh, quarks in the inverse. The down quarks vice versa must be these flavor rotations are exact symmetries if only strong construction are looked at. Not really exact symmetry of the inverse. Yeah, okay. Alright, so we have the flavor symmetry, which is basically the background behind the mathematics of it all. Make it early, we need to start another stream to restart the time limit. Oh, but I started so early, that's gonna be tomorrow. Two or more particles have identical interactions, then they may be interchangeable, affecting the physics. All complex linear combinations of these 2 particles will give the same... Hold on, I have something in my eye. Okay. There are 2 or more particles which have identical interactions, then they may be interchangeable, affecting the physics. All complex linear combinations of these particles with the same physics along this combination are orthogonal perpendicular to each other. The theory possesses symmetry transformations such as MUD, where U and D are 2 fields representing the various generations left and course below, and a unitary matrix unit determinant. Such matrices form Lie group called SU2. Of course, it's gonna be a Lie group. It's always gonna be a Lie group. Example: flavor symmetry. In quantum chromodynamics, flavor is considered global symmetry. I don't get it. How often do you think about the Polish-Lithuanian Commonwealth? Never. The answer is that question. Global symmetry. Intellectual theory, on the other hand, this symmetry is broken, and flavor changing process exists as quark decay and neutrino oscillations. This damn electroweak theory just breaking everything. Hold on, I just realized that my corner make it isn't. There we go, now we're responding. Point. Different combination. Up, down, and strange. Now, right now, yes, right now, can apply a matrix. Each of these points is just a vector with these precise 3 coordinates. The upness, the downness, and the strangeness. In this case, up and down do not refer to the position, only it's a name of a quark. It might as well have been called a red and green quark, or a, I don't know, squishy and rigid, or subscribed and liked. There is no difference, it's just a name. I just pray opponents not become stumbling ground for another world war. That would be the third time. It really would be. They should be more creative. Pick a different board. Come on, be original. Is up opposite to down, top opposite to bottom, and strange opposite to charm? Kind of. In terms of charge, yes. In terms of charge, they are. But they're not actual opposites. Actual opposites, as close as you can get to actual opposites, would be the anti-quarks. But that's still, even then, not an actual opposite. That's like more like an anti-particle rather than an opposite. I gotta go. Alright, Kevin, bye. Have a good one. No idea what that segue was, but have a good one. Good luck. The million humans think gods into magic, into boring sense with a mechanical electron radiation, the funny one spin. Since each point here is a vector, apply a matrix to it. Or, oh my goodness, that's gonna be an annoying one to explain. So the matrix isn't actually 3 quarks, is it? It's a transformation of a quark. Because it's an A. We're not back, we're back. Alright, so we're more changing them around, and that's annoying. That's really annoying. What's the transformation then? I don't really understand, I suppose. Proton quantum state is we apply one of the flavor rotations, A, to our particle, and it's a new quantum state, which we call A ket psi. Depending on A, this new state might be a proton and neutron superposition of... What is a flavor rotation then? That's what we want, isn't it? So flavor rotation is the actual thing we apply. Rotation quarks, to be more exact. Are you gonna have flavor rotation right here? No, you're not. Don't care then. Oh, lecture! That's fun. Do you happen to mention flavor? No, you don't. Cool. That's whatever. I don't care. It's really annoying. Causing quark flavors. Actually, that's a good question too. Well, I'm no difference. Train the color is for the strong interaction, the flavors is for hadrons and whatnot. The fucking deal of species like lamp. My ways, I'm not great at organic chemistry. I'm basically going through particle physics. Barely. Barely going through particle physics. That's not gonna answer the question, is it? Yeah, fudge. Can we have it as like a must? Eightfold way. Yes, what's the flavor rotation? Those physics approximate invariant. I'm sorry. Hold on for a second. Isn't that the same thing that's on the Wikipedia page? Who plagiarized who? Who plagiarized who in this case? That's the same thing. Ridiculous. This is always wild when you just find this is the yeah. Oh, that's not gonna help, is it then? Oh, I think Wikipedia might have plagiarized them because right here, transfer that some of these intents all the well, not Wikipedia, the guy who did that on Wikipedia. These flavor rotation are exact symmetries. If you oh no, never mind, it's the exact same thing. Mathaddict.net. Okay, we got this. What's a flavor rotation? By every possible flavor rotation, it turns out that the moves. What is it? Hold on. Explanation debate the role of triviality. I have two the first. Doesn't make any sense. Absolutely, it's not. Flavor physics. Basic, yeah, I'm all for it. Gimme. What's a flavor rotation? Okay, flavor space, flavor rotation. Only relative rotation by angle relevance. Do not couple to eigenstates. Oh my, okay. But what is it? Is it just us changing them around? B, beauty of the bottom quark. Discovered 977. Wait, so unitary complex geometry matrix like this. In progress. Oh my goodness. Okay, I'm gonna just send it to Reblux because that's, yeah. Looking from Vsauce. Huh. Right, Polygon. Consider me a little bit jealous, but whatever. Is you? What you? Yes, we reduce it by 9, we reduce it by 5, that reduces it by 14, which leads to 4. Physical degrees of freedom. Oh, free minus one face. Use you. I know how some can be derived. Mechanical phase, 6 phases can be observed on definition of quark fields. One total phase cannot be observed. Number of degrees of freedom reduced by 5. Feather reduced by 9. Wouldn't that mean that's 4 degrees of freedom? It is 18. Euler angles, right? Numerical values. Top goes to bottom, Cham goes to Quark. I don't get it. Hi, the lawmaker. Hi, welcome. Parameterization. We have this choice of parameters. That's not easy. That's not simple mathematics. Pardon me, but that's not simple mathematics. I've been tricked. Hold on for a minute. This is actually pretty complex. Hold on now just a second. No, this is not fine. Okay. Matrix to it. Basically, we can transform it in some way. For example, we can rotate a vector like this. There. I learned that all in high school, yeah. Make it, may I recommend some coffee? Oh, you may, and I might even listen. Bye, Kim, bye, Hagedon. Okay. Actually, due to how quantum mechanics functions, we can only rotate this point, this vector. Any matrix transform that scales it or moves it isn't allowed. The reason why is that's just how quantum mechanics works. That's just what these are, and that's just how things be. So It is then. I couldn't only rotate vector, cross was the range wise so kind of mechanical. So B. This is called flavor rotation for exactly that reason. That's how we can change our walk around. Now if we... Let me change this up right here a bit. Pure mathematical, extremely advanced, completely painful, unbearably complex, mind-numbingly tough, and hellishly hellishly unbearable. Mind-numbingly? How am I supposed to say mind-numbingly? Numbingly? No, two separate words, that makes sense. Okay. It makes me giggle, yeah. Change a walk around. Now this matrix can have imaginary numbers in it. Don't ask. And thus, if we were to graph every single possible matrix, we'd have to do it in 18 dimensions. Now, this might seem terrifying if you haven't seen my let's do physics in 7 dimensions video, but in reality it's simple. It just means that we need 18 numbers, which makes sense. 9 numbers in our 3x3 matrix, and each one can be either a real or an imaginary, so 18. Ha ha ha. Trick comes in the fact whether that we can only rotate them. The actual mathematical name for it and its effect, because it's not quite just only rotation. 8th dimension is simple. It is simple. In this case, yeah, it is, because 8 dimensions just means 8 hadrons. So in this case, it really is simple. Like if you have fruits, right? Like for example, apples, oranges, bananas, kiwis, and pineapples. 5 fruits. Then if you wanted to describe how much every other fruit is similar to these 5, you would need a 5-dimensional space to do it. Even though you're just describing fruit. It doesn't have to be actually complex in order for it to be a lot of dimensions. What's his name? It is beryllium dihydrogen flavor particle, no quark model, no eightfold way, there we go. A 3x3 unitary matrix Lie group determined 1, yeah, okay. There we go. Lie group of 3x3 unitary matrix C with determinant 1. Yeah, haven't you not seen my video, Let's Do Physics in 7 Dimensions? I made a video about this topic precisely. Okay, I'm probably challenge begin Vatican. You're not wrong! You're not exactly wrong. It is. How close are we actually? How many subscribers am I getting a day? Let's see. Nom, 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 nom. Getting 300. But that's on a high after a video. I need to finish another video to keep this up, which means 1,000 if every 3 days. A month or so ago. Oh, that's fine, I suppose. But I do need to keep it up if I want to. What does organized chaos mean? It means a contradiction. Means. Okay, there we go. And then, one. Basic idea is, since that this matrix C has to be that kind exactly, that lowers down the amount of dimensions from 18 to 8. Okay, I should probably explain. The basic idea is actually extremely simple. Really, genuinely extremely simple. Imagine a free space again. Each point on this space has 3 coordinates, x, y, z. But if we want to describe any point in 3 dimensions, we need to use 3 numbers. However, if we say that our points have to satisfy the equality of x equals y equals z, then we only get this line. It's been fun, good to stream, but I gotta sleep now. Good luck with the research. Bye, NK. Bye. Have a good one. Good luck. Get this line. Way by adding some additional information. We've just simplified our points from requiring 3 dimensions to only needing 1. Because now we can just describe point by the distance from the origin. So if I say 5, say a number 5, free space, this could mean a lot of points. Could mean points which are 5 units away in any direction, points which are 5 units away in all directions summed, could mean summed, and so on and so forth. If, however, we say 5 and we say... No, wait, this is wrong, isn't it? Yeah, this is wrong. If I say that I want a point which x plus y plus z is equal to 5, then in 3 dimensions we'll get an infinite amount of them. Any point lying on this sphere will have its x plus y plus z equal to 5. So x plus y plus z equals 5 gives us an infinite amount of them. You can't specify a single point. Well, technically it wouldn't be all of them, it would be just the positives, wouldn't it? Yeah, because in the negatives it would be -5, which means y plus z. Yeah, right. Yeah, it's wrong. How many are there actually? Yeah, it wouldn't be. Hold on. Yeah, make it. What are you talking about? It wouldn't be a sphere, would it? No, it would be it would have to be square root. Okay, let's rewrite it again. I want a point which distance from the origin is equal to 5. We get an infinite amount of them. That's because each point on this sphere is 5 units away from this origin. If you'd like to select only one point, not an infinite amount of them, you need 3 variables. It's x coordinate, y coordinate, and z coordinate. If, however, we say that we want a point that's 5 units away from the origin, and we want x to be equal to y to be equal to z, we only get 1 point. Because geometrically speaking, we want a point that's on this sphere and this line. That's how you can remove dimensions by just specifying this. This is 3-dimensional, but if we add a constraint in the form of the equation, it becomes 1-dimensional. The same thing happens with our matrices, except instead of going from 3 to 1, we're going from 18 to 8. The reason why being really difficult to explain. And right here we're just gonna link up the no, it's the wrong one. I mean this one. There we go. This channel is missing 100 videos. It's actually missing more than that. More than 100 because all the shorts. Missing a lot. I feel like that might be it for today's live stream. I am feeling a bit tired, and it's been a pretty long live stream. We did a lot. It may not seem like it, but research-wise, it was worth it. So, thank you everyone so much. Especially thank Reblax, even though it's not here. It helped tremendously. And you're happy for sticking through it, actually. Impressive. And for now, I suppose that'll be it. Thank you, everyone, so much for watching, and have a great day. Bye.